All right, so there's not that much left. There's just a few things about continuity, compactness, and connectedness, and then I will be out of your hair. Thanks everyone for dedicating like time to come here. I hope it's at all helpful and um, helps you do better in geometry than you otherwise would have if you weren't as. I hope it prepares you for it. Okay. Or I guess either if you're not taking the geometry courses, I hope it helps you with that too. Okay, so we just talked about continuous functions. So they are defined entirely in terms of open sets, and there's this thing that they're defined in the way that you talk about the pullback of open sets. This thing where you're using the inverse map. This is the pullback, where open sets are like being mapped in reverse, right? So there's like a curious notion of like, why is it that for something like a homomorphism, and maybe some other properties, there's this thing of like you're mapping forward and like you're thinking of all the structures like algebraic structures like as mapping like forward, right? And like why are we're at no point in when talking about a homomorphism in algebra do we talk about like the inverse map of, right? So why is it that in topology we want to think about the inverse map? And that's mostly because the inverse map plays much better with a lot of the operations that you do on sets, like complements of the inverse map of a set is equal to the inverse of the complement of the set, right? Like, and then I think it plays better with intersections and unions. Like you don't necessarily have like equalities here. I don't remember which way the quality goes, but if you take a set, if you take two sets and you intersect them, or maybe you union them, I forget which one, but one of these is not necessarily equal. So I'll put a question mark. This one might be true, but the union might not be true. I forget if it was actually because of the union. But it doesn't work as nicely if you don't use inverse, right? So if you did were taking the inverse, well, at least if you took a pullback, then I think it is true, right? And hopefully someone can call me out if I wrote something down incorrectly, but I'm pretty sure this is true, and like a lot of stuff works really nicely. And so we use a lot of these properties very quickly when doing proofs about continuous functions. So hopefully we'll be able to go through one of these proofs for our compactness or connectedness that uses this property, and you can see why it's very useful. But there's the other notion of like you could define this thing, and in the system I should use red. Define f is called an open map if for every open set u in x, f of u is open in y. Okay, so f is a map from x to y, right? And this is now the forward mapping thing, right? I could take a whole set here and see what happens to the image, right? But this is not, it turns out after looking at what happens, what are the results of using these types of functions, it turns out this is not exactly what we want to be to capture the notion of continuity. I think under this map, for example, like the constant map, f of x equals a single point inside of y, right? Like it's constant, right? This is all of x, right? Where you map the entire space down to a single point. We, for various reasons, we want this to be considered continuous, but it's not an open map, right? So the constant map is continuous under the above definitions, but not open. Okay. And you can see that because it takes an open set and maps it down to a single point, and the point is not open. You can't really draw a little ball that stays inside the set containing a little point. I guess I should write the set containing the single point here. So that's like maybe an example. The constant map is a continuous map. That's a nice example. Let's see some other examples. So I talked about the subspace topology. So if S is a subset of X, and I'll say it's a subspace, so we put the subspace topology on S. Then the inclusion, oops. All right, the inclusion map, which just takes a point inside of S and maps it to itself, but now considered inside the bigger set, is continuous using the subspace topology on S. Okay. And is the proof reasonable? I can at least like give the idea of the proof, which is if we want to show that the inclusion map is continuous, we have to take an open set inside of X and then look at the pullback and see, is the pullback a open set inside of S? Well, but for every open set inside of X, so for every open U inside of X, I inverse of U is just the set S intersect U, right? It's the points of S that map into U. And because this is basically just the identity function, but restricted only to S, this is true. So, and this is exactly what open sets look like, right? Inside of subspace topology. So this is open in this. So yeah, that is pretty much the whole proof. Does that make sense so far, how I proved everything? There was like a very quick one-line proof, but that is basically all the details in
there. I have a quick question. So just to make sure, in the definition of an open map, we want U to be open, right? Open in X.
In an open map definition, in this one, yeah, we want U to be open here, and then F of U is here.
Okay, thank you.
But so open maps, right? There's a different thing from continuous, just to be sure. Right. Yeah. Okay. Oh, sorry. Yes, the inclusion map is continuous. So for continuous, I'm going back, right, using the inverse map. Okay. Okay, so the inclusion map is continuous. Another fact, I should put these as, okay, usually I do like theorems and results as blue, so I'll just put a blue dot here, but this is all meant to be blue. So I'll just write fact. I'm writing fact because I never know what constitutes a lemma versus a theorem versus a proposition. So I'm just going to write fact, and they're all facts with proofs. If F and G are both continuous functions between three topological spaces, X, Y, and Z. So assuming these are continuous, so I guess if F maps from X to Y and G maps from Y to Z, and F and G are continuous, so I'm assuming they're both continuous, then the composition I'll get that out. You do F first and then you do G. Is continuous. Right. So if you compose continuous functions, you get a continuous function. And again, the proof is just, I do actually have a kind of a color scheme for proofs, which is in purple. But right, if I wanted to prove that the composition was continuous, I'm looking at a function from X to Z, so I should take an open set in Z So let U be open in Z. For every open set in Z, G inverse of U is open. Maybe I'll write it like this. G inverse of U is open inside of Y. But then if that's an open set inside of Y, then F inverse of G inverse of U is open inside of X. But then this is just equal to F goes with G inverse of U. This is just a fact about functions. It's true for function compositions. Oops. That this set is equal to this set inside of X. So this is open, and this is exactly what we wanted to show, right? This is inside of X. Right, so it works pretty well with the inverse map. Not to say that some of this stuff wouldn't work for open maps. I think the composition of open maps will also be open for a very similar proof. But it certainly does work for continuity, right? So, and this is something we kind of want. If we compose two continuous functions, it does give us a continuous function back, and that's hopefully what we would expect, right? Just by what we'd expect, I just mean like we were to if we were to think, what do we want out of something being called continuous if we were trying to define stuff ourselves, right? Okay, so another fact, the restriction map, not the restriction map, I mean the restriction of a function. Is continuous. And what do I mean, right? If I have f from x to y is continuous, then f restricted to some subset s inside of x is also continuous. And here I'm using S with the subset topology or the subspace topology. Right. And the proof is, I think, just very quickly, F restricted to S is the composition of the inclusion map with F itself. Right. And we prove that both of these are continuous, and I'm composing continuous functions. I'll just leave out a lot of the words in details, but it's the idea for the proof. But yes, so a lot of the stuff, right, like the restriction to a subspace being continuous, this is also something we want to expect out of continuity. We want it to kind of be a local property. So if we were to zoom into a smaller subset, it shouldn't break continuity anyway. So this is kind of confirming that our notions of subspace topology and continuity are kind of working correctly. Okay. All right. There's not much just on continuous, but I think they play a bigger role once we start looking at other structures that are topological. So let's go on to the next thing, which I forgot what number I'm on. I think continuity was 4. I'm just going to assume it's number 4 and go on to number 5, compactness. Sorry, if I scroll too fast, let me know and I can give something. But again, I'm going to export this as a PDF and send it out to everyone. Especially because some people said they couldn't come at the times we decided on, but okay. So once let's see. So now we have some like additional stuff on topological spaces. There's some things like compactness and connectedness. These are like additional things that are nice properties for a topological space to have. Right? And they'll be very useful, especially in the manifolds course, to know what these mean, or at least be refreshed on them. So again, just to remind ourselves of the setup, let X be a topological space, shorten it to that. And I'm just going to define what compact means. And then there's some terms in the definition of compactness, which if you haven't seen, I will define them after I write them down. But let's see. What did I use? S. Well, I don't want it to be like, it's definitely a subspace. Just let A be a subset. And A is called compact if every open cover of A has a finite subcover. Okay, so these terms I should define further. Open cover of A, sorry, and then a finite subcover. So an open cover of A is a collection of open sets, U alpha, right? And so they are open, meaning they're elements of the topology. They're just some of the open sets, and they cover A. So I guess the two properties are just that they're open and they cover A. So such that A is inside the union of these U alphas. Okay. And a finite subcover means I have that, I start with this open cover and I restrict it down to finitely many of them. Okay. That still covers A, right? So A still is inside of the union, from I goes from 1 to n of ui. Sorry. Right, and it's important that it's a subcover, so we write it like this. It's a sub-collection, meaning they all came from the original collection U alpha. Okay, and they're finite, meaning there's only finitely many of them. Okay, so if you only saw originally maybe the definition of compact in Rn, right? In Rn has a special structure of being a complete metric space, and there's a lot of stuff you can say about compact sets in how they play with the metric and completeness. But for Rn, a set is compact if and only if it's closed and bounded. Right, and bounded means that the set is contained inside of some big enough open ball. Right, I guess just go around the origin. So okay, so this notion of closed and bounded only works in Rn and some like complete metric spaces. I think it also works there. But in general, we want to formulate everything in terms of open sets, and this is the more abstract definition. And it's kind of like hard to see exactly what it's saying, but once you start using proofs involving compactness, this is really where you start to understand like why this seems to work. I don't know if I could still explain why this seems to work exactly, but it does to me feel correct for compactness, having done a bunch of proofs with compact sets. So that's all I can really tell you in terms of confidence of why this is the correct definition of compact. Okay, but whatever compact is supposed to mean, right? It's supposed to mean kind of like contained and not infinitely large or something, right? But let's go through some facts about compactness, and I think I can I will prove one of them, and maybe it'll help illuminate at least a little bit. But let me also just draw a picture, I guess, of compactness. So before I move on too far away from the definition. But let's say we have some set A, and what compactness says that is that every open cover, so let's say we had just a collection of open sets, and this could be infinitely many, probably it is if we're talking about compactness. The interesting things are, if you look at the infinite open covers, right? And so we have a bunch of these little balls covering A, and each of these is an open set. They don't have to be balls, but I'm just drawing them as open balls. What the compactness thing says is that you can reduce down to only using finitely many balls. Or I guess open sets. It should write open sets. Right, and this won't look that different, but I'll just draw fewer balls here. But the point is that there's finitely many, and before there were supposed to be infinitely many, but I can't draw infinitely many balls, at least not within an hour. Okay. Cool, so that's just a picture of it. Let's go through some facts about compactness that are worth kind of just remembering. And maybe if you have, the time, go in and see the proofs. They're not really that hard. It's just put all together. They'll take up some time, but they are good exercises of like, do I remember what, or do I understand what all these definitions are and how to use open sets again? Right, so some facts. Worth learning about compactness. So one of them was already that in Rn compact is closed and bounded, but that's specific to that one. Let's see. A closed subset of a compact set is compact. Okay, so if A is closed, sits inside of some compact space X, then A is compact. I'm just writing the short version of the statement that I'm writing, but and again, all these proofs are not too long, but I'm gonna cut them out in the interest of some time. Let's see. I guess so I didn't talk about what a Hausdorff space is, but I'm going to write down a fact that involves Hausdorff spaces. And if this is just for if you happen to know what a Hausdorff space is, and or you can look up what a Hausdorff space is. But every compact subset of a Hausdorff space is closed. Okay, in the short version, compact inside X Hausdorff implies A is closed. Okay, so Hausdorff is just another property that topological spaces can have. It's one of these so-called separation axioms. If you haven't heard of Hausdorff, then I just encourage you to look it up, but it's okay if you don't know what Hausdorff is. But it's worth looking up because every manifold, it'll be part of the definition that every manifold is Hausdorff. So if you're going to take this class, it might be worth looking up what Hausdorff space is. But this was definitely one of the things that I was going to list as like, I wish I could have gotten to explain this. But okay. So let's got anything else. I guess that's actually most of what I had for compactness. Oh, I guess a finite union of compact spaces is compact. So I'm writing CPT for short for compact. I hope that's a little clear. And also in Rn, compact is the same as something called sequentially compact, which means that every bounded sequence of points has a convergent subsequence. Okay, so this requires us to remember what a sequence is, what it means to have a bounded sequence. That just means the sequence is a bounded set if you look at it as a set, and what convergence is, right? But if you remember what all these things this is an equivalent definition of compactness in Rn. I believe it's equivalent for Rn. But it's something also just called sequential compactness, if you've heard of that. Okay. All right. So I think that's what I want to do with, oh, no, there's one that I definitely wanted to show the proof of, which is the continuous image of a compact set is compact. Okay. Meaning if you have if A inside of X is a compact set and f from X to Y is continuous, then f of A is compact in Y. Okay. So let's just go through the proof because I think it's really nice to see how this works using the definitions of continuous and compactness. Let me just write down my notes for that one. Okay. So the proof is not hard. We want to show that f of A is compact, right? So we want to show that every open cover of f of A has a finite subcover. So let U alpha be an open cover of f of A. Okay. Let's see. Yes. Then we look at this new cover which consists of the pullbacks of each set. So F inverse of U alpha. Okay. Maybe I should also be drawing a quick picture. But here's a set A. Maybe actually it's a compact set, so it kind of has some structure. Okay. Here's F of A. And then you take some cover of F of A. It's got to be infinite to be interesting. It's kind of in the way a little bit. Okay. Let's pull back all of these, and I claim that this will be a cover for A. Okay, some of these might also go way out of hand or something. But so we pull back this cover, this will be a cover of A. Then because A is compact, we can reduce to a finite subcover of A, right? So we get F inverse of U alpha 1, F inverse of U alpha n. And this still covers A, so we've dropped a few of these open balls that I've drawn here. And now there's only finitely many. Maybe I'll just erase one or two of them or something. I don't know. But it's still supposed to cover A, so we'll leave that one there. And then just look at which ones we dropped. I claim that if you go back and look at U alpha 1 through U alpha n, this should still cover f of A. Okay. So it is just, you kind of go back, use compactness here to reduce your open sets here, and then look at what happened over here. And the sets you've taken out, right, don't drop the covering property. Okay. Even though this terrible picture I've drawn, it makes it look like I've stopped covering the set, but all right, so any questions on that proof? So you can see it works pretty well with the continuity taking sets back and compactness being mapped forward, right? I think a lot of stuff works like this, which is why we wanted continuity to be this inverse directing property. Okay. Okay, so that this is the finite subcover. Okay. So finite subcover, and that works for any open cover, so f of A is compact. Okay, I think that's everything I wanted to say about compactness. Certainly, there's a lot more. If you go through and look at more proofs with compactness, you'll get a better feel for it, but at least this is a starting point, and that was my goal. Let me just... Okay. So the very last thing I want to talk about is, and I guess I'm on number 6 now, is connectedness. And this is just a similar property. Not it's similarly, it is a property that topological spaces can have, similarly to compactness. Okay. So the way I have to be a little careful with how I define it, right? I want to do it however I wrote down my notes. All right, so again, let X be a topological space. And I'm going to define the space X is called disconnected if there exist open sets U and V such that U and V make up the entire set X. U and V are disjoint, and U and V are both non-empty. So I guess i.e. X separates into a pair of non-empty disjoint open sets. Okay. By the way, this first property tells us that U and also V, they are both open and closed, right? Because, sorry, I guess both of these properties. So this thing and this thing tell us that U is both open and closed. Because both of these properties together tell us that the complement of U is exactly V, right? Because it's disjoint from U and it's basically all the rest of, right? So equivalently, you could write that there is some closed and open set that is not empty, but also a proper subset of your whole space. You might have, maybe if you've seen connectedness before, you may have also seen that definition. But this is one definition of disconnected. The picture is roughly just you. Well, okay, so I kind of need to draw a disconnected set, but the point is that you kind of draw a dividing line between two parts of your space, and you call one U and the other V, but it's hard to see in just R2. So maybe if I look at a subset of a space, so like let's maybe let's look inside of R2 and let's let X be the subspace defined by just like here's one piece and here's another piece, right? And then X is the union of these two pieces. Right. And if anyone was looking at this, they would say that X is a disconnected space, right? It's separated into at least two pieces. You could separate it into more pieces, but and then like, okay. But so for the open sets of X, right, if we want the separation, we should define open sets that separate X, and they should be clearly covering these two pieces. And so I'm gonna use green to do the open sets, right? But open sets in the subspace topology are just open sets intersected with the space. So I'm just gonna draw an open set like this, U, maybe U hat or something. And then I'm gonna do another open set V, and it's okay if they intersect in the ambient space, as long as I cover. Here's V. Oh, let me just do it in a different color. Okay. And that's also V hat. And the reason I'm calling it U hat and V hat is because the separation is going to be define the separation of the space X to be U equals U hat intersect X and V equals V hat intersect X, right? And so these are now open in X in the subspace topology, right? So I've taken open sets inside of R2 and intersected them with the space X. So U, just the set U is just this portion here, that's U, and then V is just this portion here. Okay, that was kind of done a little quickly. Does that make sense as a disconnected? So I defined what disconnected means, right? And this is why, right, you can see that U union V makes up the entire set X. So we have this first property. They are disjoint, right? Because we're looking at U and V, not U hat and V hat. And then we have that U hat and V hat are non-empty, so they are not they actually have some points in them. Right. Okay, so this is an example of a disconnected space. Right. Okay, and then just close it off definition. X is called connected if it is not disconnected. And that would be something like if I had only taken this one piece here, I would find that I can't cut it exactly into two open sets, right? If I tried to cut some region in R2 like this into two open sets by just like maybe drawing a line through here, one of these sets would have to contain the boundary, right? You can see you can't square off all three of these properties unless one of the sets is not open or something. Okay, so that's the definition of connected. All right, and so it's defined in terms of these separations into pairs U and V. So let's talk about, well, are there any questions about connectedness before I go on to just properties about connectedness that are worth remembering? Cool. Okay, so I did write, yeah. There's only two of them that I'm interested in right now. One of them is the union of a collection of connected sets which all share a point is connected. Okay, so this means if you have a bunch of connected pieces, say in R2, so this is one, and then this is another one, this is another one, and they all share this single point X. If you take the union, this will also be connected, which is something probably we would expect from connected things. If you take two connected things and glue them together along some piece that they share, the glued piece will be connected, right? And then you can take this connected piece, and then if it shares a point with another piece, right, you can glue things here and then get another bigger connected set. So you could probably extend this to a bunch of sets like pairwise connect together, then you'll get a big connected set, right? So something you might expect from the word connected. Right? Okay, and then there's the property that the continuous or continuous functions preserve connectedness. Right? Meaning if A is a connected subset of space X, you could just say if X is connected and it's equivalent and F is continuous, then F of A is connected inside of Y. Just like compact sets, connected sets also are preserved under continuous maps. Great, and then really quickly, just what is the proof? It's very similar to the idea in the compact proof. If we want to show that f of A is connected, The way we do that usually is suppose it's disconnected and then get to some contradiction, or maybe prove it. Just what is the word for it? Converse. Prove the converse. So suppose f of a was disconnected. And what does that give us? Well, disconnected gives us there is a separation, u and v, of the image f of a, right? And now we're in this situation again where we have some set here, and there's some open sets u and v. Okay, maybe I shouldn't have drawn them overlapping because there's supposed to be a separation. But the point is we have these open sets in the image and we pull them back to say something about the domain, right? So we pull back the open sets to f inverse of u and f inverse of v, and then we work over there, right? So the claim is that if you look at f inverse of u and f inverse of v, and you go through all the properties of a separation or disconnected, this disconnection or something like that, right? This will be a separation of A, and for that reason, A will be disconnected. Right, and that's the converse of the same. Right, so it's this property of carrying open sets back lets us preserve these topological structures going forward. So it seems to work really nicely, but people worked for 100 years to get this to work really nicely. So I think it's really great that they did that. Okay, any questions? I think I'm basically going to end there, if not for just writing out a few things that I wanted to mention but couldn't get to. But any questions so far about connectedness or anything else we talked about? Cool. Well, I'll just throw some terms out there. I think I didn't talk about the product topology. So that's how you put a topology when you take Cartesian products of spaces. Especially if you do infinite products, it can get kind of hairy. You have to be a little bit careful. I didn't talk about Hausdorff, but it's worth seeing a little bit of what that is and seeing a few proofs of it. It's also a little bit of a weird definition of like, why is this something that I care about? But it turns out to be very helpful in terms of separation of points. And this is maybe a separation in a different sense of disconnectedness, but it's not that different, but one of these separation axioms. Okay. But Hausdorff is another property that a space could have. So I could have a compact Hausdorff topological space. Let's see. So I wanted to talk about the closure of a set and limit points, which are the same as also accumulation points. I think these are just different names for things, or sometimes they maybe I should just write it like normal line. Okay. And then I also wanted to talk about convergence sequences in the abstract setting. Okay. But you can look into these further and hopefully, you know, that you either have the language of open sets and topologies, or you've been refreshed on them. It'll be much easier. And all of these are in Loring 2's appendix, so you can just go through there. I think that's everything for points at topology. It's a little bit of a weird subject, but I think the other ones will be a little bit nicer to deal with. But there's just like a lot of weird definitions, I think, in points at topology. So I wanted to just get through some definitions so that set up. Okay, so if there's no questions, I'll stop the recording and we can maybe ask questions like not recorded.